Welcome back to the ProCaaSo Trial Site series. Today, we will be going over the app task and learn how to control your hardware. In this video, you will learn how to understand the basics and purpose of an app task, add in the control logic for the environmental sensor, debug the control logic that you've added for the environmental sensor, and learn how to stream values from the event bus to the ProCaaSo Anywhere UI. The app task is a single Python program that will run your control logic. It is run as an infinite loop that pulls events from our event bus. Similar to the I/O task, the app task uses Python code to communicate data seamlessly between the event bus, the hardware, ProCaaSo Anywhere UI, and the time series database. Here's a quick overview of the app task folder that we're going to review in this tutorial. We'll go over the models.py file, which we learned about in the I/O task tutorial, which will store the data models that correspond to the state schemas in our system definition, the global tags.py file, which helps clean up variable usage throughout the app task folder, and lastly, the ens.py file, which is the default entry point to the event bus from the app task side of the code. Let's navigate to the app task folder in our ens package code. Open VS Code and click into the app folder. Let's walk through the models.py file for our app task. This file should be familiar as we reviewed it in our I/O task tutorial. To reiterate, the models.py file is crucial as it defines data models that synchronize with the state schemas from our system definition and facilitates attribute data communication with the ProCaaSo event bus. Notice that in this models.py file, we have the same standard configuration to set up our fully qualified name and combined model classes. This again is our recommended best practice to work with ProCaaSo. Next, you'll notice that the components from the IO1 folder are already present. Let's go ahead and add the environmental sensor data model and combined model from the IO2 folder that we added in the previous tutorial to this models.py file. We are able to go into our IO2 folder and copy our state and combined model for our environmental sensor from the models.py file and paste it into the models.py file in our app task folder. Now we have access to our environmental sensor data in our event bus from our app task. Next, we'll move on to the global tags.py folder. This file stores all of the instances of our data models for global accessibility. All we need to do in this file is add an instance of the environmental combined data model that we can call throughout the rest of the app task folder. Lastly, we will be going over the app task ens.py file. Similar to the IO task ens.py file, this file serves as the entry point for user code execution in the app task of ProCaaSo, which is crucial for initiating the application and managing data communication between the event bus. Let's walk through the pre-existing code and identify where we need to create additions to integrate our environmental sensor to the app task code. First, we import all the necessary libraries and components that will interact within our system, including the state machine library, routines for specific tasks, models for data representation, and the runtime API for application control. At the startup, our expression is set to clear any existing cache, retrieve runtime events, and importantly, initialize our state machine. We proceed to create and configure state objects for our state machine. Each state is given an ID and initialized with routines from our routines.py file. This setup allows us to define specific behaviors for different states of our application. For each state, we define possible transitions and associate specific routines. This is crucial for maintaining the flow and logic of our application as it reacts to different conditions and inputs. Next, we add necessary instruments to our state machine. These instruments represent different components of our system that will monitor or control. With that said, we will need to add the instance of the environmental sensor that we created in the global tags.py file here. Lastly, for the startup expression, with all states and instruments in place, we start our state machine in the predefined initial state, initially the idle state. If you're interested in diving deeper into the usage of the state machine, we encourage you to reach out for in-person training. Our team is ready to provide you with the guidance and support needed to master this powerful tool. Following the setup, we define expressions to handle specific data interactions. First, we read data. Expressions are set up to read data from the event bus and update our state machine accordingly. We can see in the batch data read method, we are able to access our instrument data using the state machine with the get instruments method for both the command and state attribute data. This is similar to the sensor data read function below. Let's retrieve the environmental sensor data by using these functions as an example. We start by defining env data read, a function marked with app.expression order to. The order indicates the priority of this expression within our application, with lower numbers executing earlier. Within the try block, we access the state machine to retrieve the current data model of our environmental sensor. We use the getAttributeState method from our client, specifying the data type and fully qualified name dictionary, which provides the precise location of this data on the event bus. If the data retrieval is successful, we immediately log the environmental sensor readings using logger.debug. This step is crucial for real-time monitoring and debugging, allowing us to ensure that the environmental sensor data is being fetched and recorded as expected. Should there be any issues in fetching the data, such as connectivity issues or configuration errors, the catch block logs an error, and the error logging helps us quickly identify and rectify issues, maintaining the reliability and accuracy of our environmental monitoring. Next, we execute logic. This is where the control logic utilizes the data that we had just fetched from the event bus to perform necessary operations. We start by defining main, a function decorated with app.expression order 3. Within the main function, we attempt to execute all routines previously defined during the state machine's initialization. The routines are typically where the control logic of your hardware would live. You are able to use the data pulled from the event bus for further processing if desired, but since we are just adding the environmental sensor and only want to record the environmental sensor data, no additional code is necessary. The try except block captures and logs any exceptions that might occur in the execution of our routines. Lastly, we write data. Finally, updated data from our state machine is written back to the event bus, ensuring that all parts of our system remain synchronized. First, we define env sensor data write. Within this function, our main goal is to write the latest data from the environmental sensor back to the event bus. This is achieved by using the post attribute state method from our app.client, and this method is crucial as it ensures the sensor data is shared across the platform. The data to be submitted is accessed from the state machine's instrument dictionary for the environmental sensor, specifically SM, get instruments, and state data. We also need to specify the fully qualified name dictionary, which tells the event bus where exactly this data should be stored. This is done by using the sm.getInstruments env state fully qualified name dictionary, ensuring that the data is mapped correctly in the system. Again, error handling is integrated to manage any issues that might occur during the data submission process. Now, we're going to validate the integration of our environmental sensor into our app task. Our primary goal is to ensure that the data is flowing correctly from the IO2 task to the event bus, and subsequently to the app task. Let's proceed with the tunneling and debugging procedures we covered previously. Begin by opening your tunnel, and if you need to refresh your memory on how to do this, please refer back to our previous tutorial. Next, navigate to the debugging tab in your development environment, and we'll start by tunneling into the IO2 task as we've done before to confirm that data is correctly being captured on the event bus. Make sure that you're working in the right context by selecting the correct folder. Choose the Python run ens.py under task IO2 from the drop-down menu and hit play. Observe the temperature and humidity readings output to the terminal. It's essential to keep this debugger running to ensure that continuous data flow is available for the app task. Before we start debugging the app task, double check that you've selected the correct project folder, and now choose Python run ens under task app from the drop-down. Hit play to begin debugging the app task concurrently with the IO2 task. As we navigate the debugging process, notice how both debuggers operate in tandem, ensuring that the data synchronization between the I/O and app task is maintained. Fantastic! Our observations confirm that the environmental sensors being processed by the IO2 task are successfully transferred and mirrored in the app task. This successful integration highlights the efficiency of our tunneling and debugging setup, ensuring that our application is robust and reliable. As we successfully verify the functionality of our code and the data transmission across our tasks, our next step is to stream these values from the event bus directly to our ProCaaSo Anywhere UI. This will allow us to visually monitor the environmental sensor readings just like we do with the distance sensor values. Let's begin by logging into ProCaaSo and navigating to the trial site follow-along system project. Once inside the project, let's open the system definition and scroll down to the temperature and humidity component. In the visual section of the temperature and humidity sensor, you will observe 3 flares: humidity PV, name label, and temperature PV. These labels are integral to our HMI display. Each label currently has an input attribute set to none, suggesting no dynamic data linkage. However, we want humidity PV and temperature PV to display real-time data from our sensors. Let's update the input values for dynamic data streaming. For the humidity PV attribute, we will type .stream.thermohygrometer.state.humidity. This links the humidity PV label to the humidity data from the thermohygrometer instrument, specifically accessing the state's humidity value from the event bus. For the temperature PV attribute, we will type .stream.thermohygrometer.state.temperature. Similarly, this links the temperature PV label to the temperature data from the thermohygrometer, pulling from the state's temperature value from the event bus. Let's save these changes and return to the HMI view on the systems page. Now, let's go ahead and open the debugger for both of our I/O tasks and watch the values on the HMI. The labels will no longer display a static default value, but will update in real time to show the current temperature and humidity readings from the environmental sensor. This ensures that the display temperature is always current, reflecting the latest sensor data. Thanks for joining today's session on the app task overview. Stay tuned for our next tutorial where we will go over how to package your ENS code and deploy it to your system in ProCaaSo. See you next time.